All righty, we're going to talk about section 1.5. A lot to get to here, so we'll have to kind of talk and get through it. But we're analyzing graphs of functions. And so a couple things, we've sort of talked about this, but the zero of a function, so if you ever have a zero of a function, y equals f of x, you basically are just going to set equal to 0 and solve it. So if you ever ask you, hey, find the 0 or zeros, that means basically set equal to 0 and solve. So it's another way of saying what's an x-intercept. So okay, that's the same thing as saying find the x-intercept. So we're just going to replace f of x or y or g of x or whatever it is equal to 0. So this first one, 0 equals 2x plus 8. We can go ahead and solve this equation pretty quickly. Subtract 8 to both sides. Being a linear function, if it was quadratic, we'd do something entirely different. But we know how to do this from algebra. Divide both sides by 2, and that would give you that x would equal a negative 4. So the 0 is negative 4. That's the value that if you evaluated it at that number, you would get 0. It's also, if you looked at the graph of that equation, you'd end up with, it would be crossing the x-axis at negative 4. Same thing here. If I set this equal to 0, this is a quadratic. We can't solve it like we solved a linear equation like we did in the last one. So that means that I have to go ahead and factor this one. So if I have two categories, as I've done before, it's going to multiply to a negative 24. It's going to add to a negative 2. And so if you want to write out all those different factors like negative 1 and 24 and 1 and negative 24, those don't work. And then negative 2 and 12 and 2 and negative 12. Those add up to 10 and negative 10. And then negative 4 and 6 and 4 and negative 6. And those do work because we want this pair. So then that would give you x plus 4 and then x minus 6. Now, as we've learned how to solve these before, when we've done x-intercepts, you have to set each of these equal to 0. So I have to say x plus 4 equals 0, and then x minus 6 equals 0. If you go ahead and solve it, you'd subtract 4 here, so then that would give you a negative 4. And then here it would be adding 6, that would give you a positive 6. So the two values that if you plugged in x equals negative 4, that would give you 0, and if you plugged in x equals 6, that would also give you 0. So those are your two x-intercepts as well. This one is a little bit different. I'm going to go ahead and solve it here. The only way to get rid of something that's being square rooted would be to square it. Those are its opposite. So I can take this, square that, take this, square that. If I did that, that would give me 0 equals 25 minus x squared. And now we'd have to subtract this 25. So that would give you negative 25 equals a negative x squared. So I'm going to say that's a negative 1. So if I divide this by negative 1 and that by negative 1, that gives you 25 equal x squared. And if I go ahead and now square root that, because that's the inverse or the opposite of squaring, that would then give you two answers. It would give you a plus and a minus 5, not just a positive 5. So when you square both sides, you have to think of the positives and negatives. Because if I take this number 5 squared is 25, but negative 5 squared is also 25, because negative 5 times a negative 5 is a positive 25. So this is going to have two x-intercepts, but it's really easy to say that there's only one based upon that. So that's how you find the 0. Next thing we're talking about is looking at a graph and looking for increasing and decreasing functions. So this graph right here kind of represents this. And we always read a graph from left to right. So I'm reading it from left to right. This graph is increasing. It's going up as I read it from left to right. Constant means it's staying the exact same height. This is height of 1. And then the next one, this is increasing from here to here, and then it decreases. The other thing when we're talking about this with interval notation is we're basically having to go from here to here. Now, when we look at these values that it's increasing, we're basically saying that this is increasing from negative 5 to a negative 2. So from here to here on the x-axis, it's increasing. From negative 2 to 1, it's staying constant, or excuse me, negative 2 to 1. That from 1 to 3, it's increasing, and then from 1 to, in this case, 5, it's decreasing. So we're only worried, when we do these intervals, we're only worried about the x values of them. So the y values are telling me, hey, are they increasing, decreasing, constant? But the x values, we're going to use interval notation. We can definitely use infinities here, depending if the arrow is going, as we'll talk about. So determine the intervals which this graph is increasing and decreasing. So if I kind of look at this roller coaster, like I kind of like to liken it to this thing, first off, I'm cutting off the screen. This thing's coming from down here, which we'll talk about. But this is going up. It peaks here. It goes down. It kind of troughs out there, and then it goes back up. So this has 3 different intervals. So this thing is increasing, then it's decreasing, then it's increasing. So I've got a couple of different intervals. So I'm going to make a couple for each one. So increasing, it's supposed to say increasing. So this thing's increasing from way over here. So this is actually coming way from the left. So even though there's not an arrow there, technically speaking, it is an arrow, same thing on here. And so this thing is coming from negative infinity. So whenever we're using interval notation, parentheses is always going to go around anything like that. Now, the other thing that we're going to kind of do is anytime we deal with intervals like this that are increasing or decreasing, these are always parentheses. But we're using interval notation, so we're saying it's starting at negative infinity, comma, and then it's going to go to this value here. Now, we're only concerned about the x value, so that'll be till -1. We're not concerned about this 7. The 7's telling us it increased from way down here up to here, but we're only worried about that. Then from this point to this point, from -1 to a +1, it's decreasing. So -1, 1. That doesn't mean the point -1, 1. That means from an x value of -1 to an x value of a +1. And then this thing is increasing again. And it's starting at that 1 value, and then it's increasing as we go to the right forever and ever and ever. So that means it's going to go from 1 to positive infinity. And so some people like to put increasing like next to each other, and then so they have one increasing and one decreasing. This had no constant. It wasn't staying going straight across or horizontal at all, so I don't have any of those. And sometimes you only have one thing going on. Sometimes in this case, I have 3 different intervals. Sometimes there's only one. It just depends on your function that you're looking at. Here's an example that on this one, as I read this thing from left to right, it's just increasing the entire way. So this thing is going up forever and ever and ever and ever. So when I say increasing, that's just from negative infinity to positive infinity. So sometimes there's only one thing going on as opposed to last example. Last thing, the points at which a function changes its increasing, decreasing, or constant behavior are helpful for determining the relative min and the relative max. So relative min is meaning in the area, it's a low point, it's a minimum. Relative maximum, or relative max is in the area, it's the high point. And we're talking about this. Now, to kind of go back to a couple of examples, if I go back here, this point, that was the high point. This is what we would call a relative max, because in the area, it's the highest around, because this thing switched from increasing to decreasing. Down here, I was decreasing and then it switched to increasing. That was a relative minimum. So whenever you kind of have a change in direction, you're going to have something along those lines. So that's what that's talking about. So it says find the relative min max. So if it gives you an equation, put it on Desmos. And on Desmos, all I did was just click these high and low points. Now this point right here, that's not changing direction. That's still decreasing. So that doesn't help me, even though I could find that. But in this case, we're only worried about that. So we have a relative min and a relative max. So this point right here, in this coordinate point, this is a high value. So it's going from increasing and going back down to decreasing. So we call that a relative max. So I have a relative max, if I could spell it correctly. So I've got a relative max, and that's at the coordinate point -1, -2. And then I have a relative min, and that's down here. So this one, it was decreasing and then it switched to increasing. So there's a relative minimum. So in the area, it's the lowest, 1, -6. Another way of saying relative min or relative max is always local min, local max. So it uses those things as well. And then the last thing to talk about, just again, a reminder on that last example, if it gives you an equation, just use Desmos, click those points. Remember, there can only be 1, there could be 2. If it's something like this, they have none. The answer would be no relative max, relative min, because it's not changing direction. And the last thing we'll talk about even odd functions pretty briefly. A function is said to be even when its graph is symmetric with respect to the y-axis. So if you kind of take this graph, if I drew a line right here, if you folded the right side over that line, it would match up perfectly. So if you have symmetry with respect to the y-axis, we call that an even function. And there's also a little property here that if I plugged in any negative x value, I'd come out to get the same thing like a positive. So if I plugged in f of -2, it would be exactly the same as if I did f of +2, or f of -15. I get the same answer as f of +15. A function is said to be odd when its graph is symmetric with respect to the origin. So basically, what I think of that, I think of kind of following along, two different things. If I kind of reflect this over my y-axis and then reflect it over my x-axis. So I take this, reflect it over here, then reflect it downwards over my x-axis. If that matches up perfectly, then that has symmetry with respect to the origin. And so the other property here is f of -x equals negative f of x. And so that's just something to kind of know with regards to symmetry.